In this lecture, we will discuss about projective geometry and its application for the analysis of images in computer vision. As earlier during the discussion of fundamentals of image processing, we have seen how images are formed in a camera. So, here you can see the rules of projection is that given a scene point, then from that point you can draw a ray which passes through the center of the lens, and then that ray, when it intersects the image plane, then that particular point is the image point of the three-dimensional scene. And this perspective projection rule is applied for any scene point. For getting the image point of any scene point, you take another scene point here, and once again let me draw a line passing through the center, and when it is intersecting the plane of projection, that makes the image point of the other scene point. So, in this way the projections are formed. So, what we can see that this particular geometry can be well understood or well studied in the case of using projective geometry. So, let us understand what is a projective geometry. So, these are the things for scene point. So, there are usually in the mathematics we study our geometry in the real space, in our school book geometry or later on in the analytical geometry. Consider a two-dimensional space where any point in the two-dimensional space is denoted by a particular pair of coordinates, x and y pair of coordinates, and since this is the Cartesian product of real axis, we denote this two-dimensional space also as r square, and this point belongs to the two-dimensional coordinate space. Following this coordinate convention, there is a origin, and there are axes, x axis and y axis, based on which these coordinates are correspondingly defined. Now, when we are considering a projective space, once again a projective space in two dimension, but implicitly there is a three-dimensional space behind that definition. It's like an image. When you look at an image, all the points in an image, they are in a two-dimensional plane, but finally those points are related to three-dimensional points in the scene. So, if we apply the rule of perspective projections, you can, in this case, what we can consider that in this three-dimensional space there is a point which is the origin, and if there is a ray passing through this particular point P, then that ray forms the that ray itself is representative, as if this point is representing this ray itself, and any point on this ray is equivalently represented by particularly this representative point of two-dimensional point. So, this is what is a point in a projective space, and we call this space as a two-dimensional projective space. So, you should note that if I take any other point in this space, then once again if I draw a line passing through the origin and extending this ray, so the whole line itself is represented by the point in this plane. So, this is what is the two-dimensional projected point, and every point in this particular plane is represented by this in this form. So, every element in this plane, every point in this plane is actually representing a ray. That is the basic representation of a projective space. So, in this case a point x y 1, it is a canonical representation of the projective space, where you have a three-dimensional plane, three-dimensional coordinate system, as you can see implicitly this three-dimensional coordinate system, as if this plane is at a distance of 1 along the z direction, and all the coordinate axis in this plane is also parallel to the corresponding coordinates of the implicit coordinate system of the 3-dimensional plane. And if I consider any point in this plane, in this ray, so that is also represented by the proportional factor of k. Any point can be represented where k is a parameter. So finally, a point x y in a 2-dimensional real space is equivalently represented in the 2-dimensional projective space as a point set of points k x, k y, k, where k varies, which is actually representing this ray. So this is a relationship when we consider an image as a 2-dimensional real space, and on the other hand, when the image is considered as a 2-dimensional projective space under the imaging perspective of projection. So this coordinate system is called homogeneous coordinate system, and you have an additional dimension which is denoting the scale of this coordinate system. So if all other coordinates are divided by this scale, you will get the non-homogeneous representation which has direct relationship with the 2-dimensional plane. So let us understand bit more about this homogeneous representation. So let us consider a point in R square, which is a real space, the ordinary space which we are used to understand in our geometry. So let us consider a point x. In this case, I am using this notation vector to denote that it's a tuple. In this case, it's a 2-tuple coordinate systems. So it's a vector also. You can represent this also as a column vector of coordinates, and this is a representation I will follow throughout in this lecture. So let this point be this. So the corresponding point in the projective space is denoted in this form, and here also you can see that it's a 3-vectorial representation where you have an additional dimension which is denoting the scale and which is multiplied with all other coordinate system. So these two are equivalent representations in our perspective. Either I can denote a point as a 2-dimensional, as a point in a 2-dimensional real space, or a point in a 2-dimensional projective space with 3 coordinate dimensions. And you can see one of the interesting facts in this projective space, that the origin of that space is not included, because if you would like to draw a line from origin to that was the definition. So it is a singular point. You cannot form a projection ray from between two at that point itself. So it's a singular point in this space which is not included as a set of points in the projective space. So I can consider that any point in the space of 3-dimensional real space, excluding the origin, they can be represented as a point in the projective space. However, you should understand the elements in the projective space are not points, they are all rays passing through the origin, and each ray can be mapped to a point in a particular plane in that space. So this is another example what we would like to understand once again, that consider a point in the projective space given in this form, say 25, 30 and 5. So what should be the corresponding point in the real space? So in this case, how do you convert it? As I mentioned that there is this additional dimension which is representing the scale. So to convert into the real space, what I need to do? I need to simply divide these coordinates by this scale, and then we can get the corresponding real space point. So this is how these points will look, that you can get you divide it by 25 divided by 5, so it should be 5, and 30 divided by 5, which is 6. So, this point is equivalently represented by 5 and 6 coordinates in the real space. Let us also consider another tricky situation. Suppose I am considering a point 0, 0, 0 in the projective space. What should be the real point in the real space? But as we have discussed that this is not included, so this question is not valid, because no, this is not the point in a projective space. So, I cannot convert these points. As you can see that 0 by 0 is also undefined mathematically. So, it is consistent with mathematical notations and operations. So, this is not a point in the projective space. So, I cannot consider any equivalence point of this in the real space. So, it does not belong to the projective space. Let us understand another fact, that is homogeneous representation of a line in a plane, and let us see how the lines are represented here. Say once again you consider a two-dimensional real space, and P is a point, and consider a line between this point, which is represented by our familiar equation of line, straight line equation, Ax plus By plus C equals 0, where A, B, C we know they are parameters of the straight lines. Now, this representation itself, what I can consider that A, B, C, this parameter, that itself is representing this straight line, and we know actually instead of 3 parameters, 2 parameters are sufficient, because this is the proportional ratios of A, B, C that is uniquely identifying a particular straight line. So, what I can consider once again like there is a projective space, a different projective space which is representing only lines in this case. So, a line in this two-dimensional space is represented by a point in this projective space, and following the same representation. So, you have a three-dimensional implicit three-dimensional coordinate system. It is a two-dimensional projective space once again, and if I consider any element of this space, that should be a ray passing through the origin, and incidentally if it passes through this particular point A by C, B by C 1, that is what is a representation of this straight line. So, a straight line is represented like a point in this space. So, it is an element as I mentioned, and any point. So, whether it is A, B, C or whether it is K A, K B, K C, all are straight lines. So, as you can see, the third dimension is again representing a scale for representing this element straight line. The fact we can denote this relationship of straight line into this form, which is as you can, which is a it's a dot product of the two vectors, or we can say it is a matrix multiplication, where this is represented as the transpose of the column vectors of the projective point, and this is a straight line vector. In a simple form, I can represent in this way, that this is a point containment relationship, and this representation in a simple form we can represent it in this way. It is a transpose of the column vector of the point x, and also it is multiplied with the column vector of point representing the line, and that is equal to 0, which is essentially representing the straight line equation. I can write this equation because these mathematical operations can be also equivalently represented as transpose of L dot x equals 0. So, in this way you can see that whether it is point containment or that equation can be represented in this. So, points and lines in in the projective space have nice complementary relationships. We call that is a kind of duality relationships. So, what we are looking at in this particular case, we will explain the duality relationships, dual relationships. So, any point in the real space or any line in the real space can be defined by 2 points that we know. 2 points define a line. So, uniquely define a line. And similarly, this operation can be expressed, this line can be computed as a cross product of these 2 3 vectors. So, x1 is representing the corresponding projective homogeneous representation of point x1, and this x2 is the homogeneous representation of point x2. So, there are 3 vectors. So, if I take the cross product, actually you will get this straight line. On the other hand, in the real space itself, any point is also defined as intersection of 2 straight lines, and which can be also computed, which has the relationship in the projective space is in this form. Here it is a cross product of these 2 lines which are represented in the projective form, and then we are getting the corresponding point of the corresponding intersection point, that is also represented in the homogeneous coordinate system or as an element of the projective space. Here you should note that how the cross product of 2 vectors are defined. This is the usual usual mathematics that we learned in our school book. So, you should see that x1 corresponds to the coordinates and these are coordinates corresponding to point x1, and these are the coordinates corresponding to point x2, and once we define the cross product of 3 vectors in this particular form. If I get the determinant, then I can always compute this point if we expand this particular determinant. So, this is a summary: exactly one line that passes through 2 points and exactly one point at the intersection of 2 lines, and their relationships in projective space, they are quite similar. A straight line can be expressed as cross product of these 2 points in the projective space, and a point can be expressed as cross product of these 2 straight lines. In again, all representations are in the projective space. So, one of the interesting applications would be to find out the straight line passing through 2 points by applying this method. We have learned this method from simple coordinate geometry, but we can see that these computations can be very briefly summarized using this operation of cross product in using the concept of projective geometry. So, let us consider this particular problem, that we need to find out a line passing through the points 3 5 and 5 0 in a plane. So, naturally it is understood that 3 5 and 5 0, they are the points in a 2 dimensional real space. So, what we should do in this case, what we will be considering, that we will be taking the cross product of the corresponding projective points in the projective space of 3 5 in the homogeneous representation, and that vector and also the vector which is represented from this point in the projective space, which means the vectors say 3 5 1 and cross product of 5 0 1. Okay. So, that is what is the straight line representation. So, if I expand this, let me do this sum. So, as I written earlier, so we have these particular components, and you are representing so these are the unit vector directions, as you know, and represent with the corresponding vector components. So, if I expand this determinant, what I need to do? I need to consider this sub determinant into E, which means say 5 minus 0 into I plus, then you suppress this and then you take the determinant, and you have to take the negative of that. So, 3 minus 5. So, I should write here this is should be minus, then it is 3 minus 5 j, and then you suppress, you consider this part of the subdeterminant for the kth component, and you take the determinant, which is 0 minus 25 k. Okay. So, this should be then 5 I and this should be plus 2 j and then minus 25 k. I hope my computation is correct. Let me see with the result and you should also verify it. So, finally, this line is represented by a vector, as you can see. I will take from 5 I 5 from 2 and this is minus 25. So, if I write the equation of the straight line, what should be the equation? 5 is that A, 2 is that B and minus 25 is that C. So, the equation of the straight line can be represented as 5x plus 2y minus 25, that should be equal to 0. So, that is what is your equation. Okay. So, let us see that how this result is So, this is a summary of the result. So, as you can see, we will get this equation 5x plus 2y minus 25 equal to 0. That is the equation of the straight line in our understanding of coordinate geometry. Let us do another example. Consider this. So, we have computed the line from 2 points. Now, let us consider there are 2 lines and we would like to compute the point of intersection of these 2 lines, and these 2 lines are given by these 2 equations. So, once again let us work out. So, from this line, so now what is the rule or what is the what kind of operations we have to do? So, the intersection point, if I consider the intersection point is say P, so that would be is a cross product of these 2 vectors L1 and L2, where this will represent L1. Let us see how we will do it, and this line will represent L2. So, from 5x minus 2I plus 4, we know that L1 can be represented as, say L1 is represented as 5 minus 2, 4, this is a representation of L1, and 6 minus 7y minus 3. From there L2 is represented as 6 minus 7 minus 3. So, we need to take cross product of these 2 operations. Once again, I will consider the same determinant I, j, k, and this would be 5 minus 2, 4, this is 6 minus 7 minus 3, and then if I expand it, what would be the expansion? So, let me rub some areas. Okay. So, if I expand it, let us consider it. I will be expanding in this way. Say this coordinate, this subdeterminant, that means this and this, it is plus 6 and then plus 28. Okay. So, I am doing it mentally, 6 plus 28 I, then plus, or I should put it as minus, then this middle determinant suppressing the middle column, it is minus 15 and then minus of 24. Okay. And then we consider the third component, which is minus 35 and minus, this is minus 12. So, it should be plus 12. Okay. Minus 35 minus of minus 12, which is plus 12, that is k. So, the full now this coordinate can be represented as this expansion can be say 34 I minus this is 39 j plus 23 k. Okay. So, what is P? P is represented as this vector which is 34 minus 39 and this is not plus, this is minus 23 and this is minus 23. I hope my calculation is correct and let us see. So, as you can see, this is the homogeneous representation of a point. Actual point, what you need to do? You need to divide this scale value, you need to divide all the coordinates values with this scale value. So, let us find out that what is the result of this operation. So, you can see that that is what we are getting 34, 35 minus 23. I am not sure whether I just rubbed it, but as I mentioned this scale value has to be correspondingly divided by 23. So, this is the coordinate that we will get. You have to check my computations once again, there could be some error there. Let us then complete this lecture by explaining the duality principle. As we can see, the point and line, they are represented in the projective space and their relationships, they can be nicely complemented by each other. For example, if I get the containment relationship x transpose L equals 0 and then L transpose x equals 0. So, you can see that whether if I interchange also L and x, still this relationship holds. That is what is the duality principle. Not only this point containment, if I consider the cross product, if I point in line intersection and point intersections which are expressed by the cross product operations of 3 vectors. So, in this case the cross product of 2 lines L cross say L prime gives you the corresponding point and cross product of 2 points x and x prime gives me the corresponding line. So, once again the places of lines and points if you interchange still you get the same principle. So, that is what is the duality principle. What it says that, so to any theorem of 2-dimensional projective geometry there corresponds a dual theorem. So, this is any theorem and then there is a dual theorem which may be derived by interchanging the role of points and lines in the original theorem. So, with this understanding of duality principle, let me stop here at this point. We will continue this lecture in the next video lecture session. Thank you very much for listening to my lecture.